Hi, my name's Adam Langley from Villanova University, and Anthony asked me to talk about context dependence in global change experimentation. And that's what I want to do. I can't do it comprehensively. I'm just going to do it through my own particular lens, which is largely shaped by wetland ecosystems, as you see pictured here. In the background, we have an herbaceous marsh in Florida, which is rapidly being overtaken by mangroves. So we have this dramatic background shift that's going on top of which we impose our manipulations. But there's really nothing we can hope to learn in this ecosystem that isn't strongly influenced by this big shift that's going on, this conversion from a grassland to a forest. That's going to affect everything else that happens here, and in fact, it's going to determine the very existence of this wetland in the future. I wanted to give you the take-home point up front, just in case your stamina runs out. I can totally forgive you for that. With ambient change is the term I use to refer to background change in an ecosystem, aside from the treatments you're imposing. So, as global change experimentalists, I feel like I've been guilty of this thinking in the past that we want to choose a kind of pristine ecosystem to do our experiment in, and then hammer it with our treatment. And often when we're trying to compare across these studies, we just isolate the effect size because they're noisy. Ecology is noisy. We want to minimize that noise and maximize what we're looking at, and that's understandable. But I'm arguing here that we need to recognize the change that's happening around us. The world is in upheaval, and it's really, really difficult to ignore that now. And we should reference these treatment effect sizes to the magnitude of background change that's occurring. That's one very useful metric. We can hope to use these experiments maybe to figure out what's driving this background change. So I think there's a lot to be gained by kind of broadening our perspective about these experiments and what our controls mean. I'm going to give you some examples of background change and how it modifies the overall response of an ecosystem. So this is the Smithsonian Global Change Research Wetland, we call GCREW. And we have a slew of different experiments here. All of them manipulate CO2 along with many other variables. And we've seen that a lot of these manipulated variables influence the magnitude of the CO2 response of the ecosystem. But more and more, the longer we run these experiments, we also see that background variability in abiotic drivers or anbiotic drivers can also strongly modify the CO2 response just within this one kind of little ecosystem. So first, here's an example of how our other treatments can modify the CO2 response. And this one is very counterintuitive. This is one of our earliest observations from the CO2 by nitrogen site at GCREW. Where we added nitrogen, it greatly stimulated the growth of C4 grasses to the detriment of the C3 sedge. And so adding nitrogen actually suppressed the CO2 response of the whole ecosystem. So this drove home the first most important point here, that plant community composition really is important for determining ecosystem function. We see this no matter what ecosystem response we're looking at. In these ecosystems in particular, and probably all around the world, a subtle shift in plant community can cause a huge change in ecosystem response. This study, in 2010, that paper was talking about the CO2 effect. It could be elevation gain, which sustains these coastal wetlands, or recently we've seen the same thing with methane emissions and many more studies. But as we ran this study longer and longer, we saw that, wow, that initial stimulation of grasses where we added nitrogen, so the blue and green lines, say, peaked around 2008 and then have diminished ever since. We saw that huge, strong stimulation, thought we figured it out, and then everything changed. As these grasses have just continued to diminish, they've gone locally extinct from many of our plots. Meanwhile, the sedge, the C3 sedge, has continued to increase in abundance. So one of the points here is just that in the long term, you see these reversals that you just cannot predict from short-term study. One of the great advantages of these coastal wetlands is the simplicity of these natural ecosystems. In these plots, we only have 3 species. And so it was pretty clear what's going on with that sedge increasing in contribution to total biomass is that it's more flood tolerant. And we've had an acceleration of sea level rise. You can see here in the blue is kind of the decadally integrated rate, which is over 7 millimeters per year, compared to the longer term rate, which is less than half that. Here's a picture of the marsh flooded on the right. So as we had sea level rise, that really the grasses just can't handle it as well as the sedge. On the left here, you see the grass biomass in the top panel and mean sea level integrated over a couple of years on the bottom panel. And that's really, there's no mystery here. When sea level rose, the grasses kind of tanked. And so whatever resource effects we were seeing, we had this interesting interaction between CO2 and nitrogen stimulating grasses. Sea level is dominant to those effects. So it's a pretty clear case where this abiotic stressor of increased flooding was suppressing any resource effects that we might see. We've seen the same phenomenon with CO2 effects at this site. CO2 ultimately causes warming, which causes sea level rise, and elevated CO2 also stimulates plant growth. But sea level rise seems to interrupt the mechanisms by which CO2 stimulates plant growth at this site. So ultimately, this system kind of short circuits itself, and sea level rise really ultimately overrides any resource effects on plant growth. So the CO2 effect is real here, but it's overwhelmed by other treatments, and it's overwhelmed by this thing happening in the background, sea level rise, which is just dominating all other effects. So we have sea level rise as an obvious dominant agent of background change. Another one here is a Phragmites invasion. If you look at the picture on the lower right, you can see the kind of the stands of fuzzy vegetation. That's Phragmites invasive. This is Eurasian Phragmites that's overtaking this marsh. And when it comes in, this is you're converting a very low stature herbaceous grassland into what's kind of a forest almost. You can get frag that's 15, 20 feet tall. Changes everything about that ecosystem. We can measure CO2 effects in these chambers. We set these chambers up along the invasion front of Phragmites so we could capture the progression of this invasion and see how it changes things. We also measure parameters in the native side versus the fully invaded side of these plots. So we can compare the resource effect to the background effect of what's going on with this invasion, what I call here the plant species effect. And what we see is the effect of the invasion far outweighs any CO2 effect. So it doesn't matter how this native marsh vegetation is responding to CO2. Everything about this ecosystem is going to change when that frag marches through. Now CO2 and nitrogen, which we have in this experiment as well, can modify the rate at which that happens, But the CO2 effects in this native pristine marsh don't matter when frag marches through. One other system I want to mention is another wetland, coastal wetland down south. This is in Florida, where because of declining frequency of freeze events, mangroves are starting to colonize and take over wetlands down there. It's very similar in many ways to Eurasian frag invasion in northeastern wetlands. Down here, you're, as I mentioned before, you're converting this marsh into a forest. You can see the panels on the left and the right. On the left, you have a little green patch at the top, which are some baby mangroves, and by 2019 on the right, you see that patch has extended and you've got lots of large mangroves. And what you can't see in this marsh are embedded many, many mangrove seedlings. So by another decade, this is going to be a forest. And this is work in collaboration with Samantha Chapman here at Villanova. We did a passive warming experiment out here to look at the influence of chronic warming on marsh and mangrove plots at 3 sites along this ecotone. And we were able to measure some warming influence, but the warming influence is completely trivial compared to the influence of the invasion that it's causing. So you have this direct effect of warming on ecosystem function, and you have the vegetation mediated, the influence of warming mediated by vegetation change, and that far outweighs all the direct influence. It's important to note that this vegetation shift, because of the way it's happening, and it kind of gathers this inertia, and it really occurs across the landscape scale because of the way that these mangroves propagate themselves. It's not something that you could detect in a plot level experiment. So it's inherently something that happens at a larger scale, and it's hard to simulate in an experiment. So all I conclude so far is that ambient change, whether by sea level or invasion or climate change driven vegetation shifts, rain shifts, is very difficult to ignore in my own experiments. And these are coastal wetlands. They may not perfectly represent the rest of the world, though I often try to argue they do act as a harbinger of what's to come. But they're different. They're tend to be more species poor. They tend to have a heavy influence of abiotic change, right? Sea level rise is a very dominant abiotic driver. So how generalizable is this pattern? Is ambient change important everywhere? And so I really didn't know what to expect, but I got to working with Megan and Kim and the rest of the core team and looking into their wonderful database where they have plant community or species level plant data from well over 100 global change experiments all over the world. So I will talk about those results in a second. I also wanted to mention the MESI database that Sebastian Lusinger's working on, where it's kind of combining other databases, and it doesn't have species level data, but it has a lot more experiments and ecosystem level responses that we're also going to be asking these same questions with. So from the core database, I got a lot of species level data from a lot of different experiments all over the world, applying all kinds of different global change treatments, and assess the trajectory of all these individual species. What I expected to see was that we're going to be, with these global change treatments, we're going to be selecting winners and losers, right? Where you add nitrogen, we're selecting nitrophilic species. So I expected to see that there would be no relationship between the trajectory of a species in the treated plot versus the control plot. So that's what I have plotted here. This is all the species included in this study. It's something like 2,000 cases Every symbol represents an individual species. The x-axis is the trajectory in ambient conditions. So if that species is increasing or decreasing, the y-axis is that trajectory in treatment plots. And you see I have 5 different treatments plotted here: CO2, water addition, nitrogen addition, phosphorus addition, and warming. And what we found was, I thought was very surprising, that if you knew what a species was doing in ambient plots, you pretty much had a good idea of what it was doing in treatment plots. So that is to say, the treatment effects weren't very strong compared to the trajectory that that species was already on. So this raised, and I have here this purple dot, I highlighted one of these exceptions where we saw a big difference between the trajectory in ambient versus that and the treatment plots. But most of them fall pretty much on the 1-to-1 line. And so that begs the question, well, what's driving this pretty dramatic ambient change that we're seeing across all these studies? Well, it could be any number of different things that to cause those patterns. It could be, we should first acknowledge that there are some natural ecological phenomena that can cause the patterns that I saw. You can have natural trophic cycles that would cause that. You can have natural climatic cycles that would cause strong background change to be mirrored in your treatments, right? Succession's a big one. We'll come back to that briefly. You could have experimental artifacts like a chamber effect might cause this correlation between ambient and treatment plots. But we know from observational data that we're having biome shift right now. We're having increasing disturbance through fire, increasing invasion. So all these other factors that are actually changing in the background. Many of them are factors that we try to simulate with our treatments. And I feel like a lot of these experiments that I included in my study and elsewhere have their own thing going on, and we kind of consider it just this one-off. Like at my site, well, if sea level rise wasn't happening, we'd still have a big CO2 effect. So there's probably a big CO2 effect globally. But everybody's got their thing. I think of Jasper Ridge. They had the fire. It's like, well, if we didn't have that fire, we'd have a bigger whatever kind of effect. But you did have the fire, and everybody's having something like that, some kind of upheaval climatically. It's something that we need to consider. You can't just interpret your treatment effects without considering that part of the bigger picture. I tried to think of some analogy for how to explain this result that I found very perplexing. And, it made me question everything about global change experimentation. Like when we're doing these experiments, are we just rearranging deck chairs on a sinking ship? I love this meme. This ship can't be sinking. My end just rose 200 feet. And I think that applies to, maybe you're seeing a big CO2 effect in an ecosystem that's drought-stricken, so that all plots are declining in NPP. But, we focus on the magnitude of that CO2 effect, not the big picture, maybe, of what's happening in that ecosystem. Anthony sent me this slide of some results from his synthesis in 2019 across 4 forest CO2 experiments, which says the same thing. It's not about individual species abundance here. It's about NPP. But one of the main conclusions was that, say at Oak Ridge, you can't really interpret the CO2 effect there without understanding what's going on in the background. And what's going on in the background there is succession, and throughout succession, you have progressive nitrogen limitation, even in ambient conditions. So you have to consider that to try to draw any generalities across these 4 experiments. So Anthony asked for a priority question. I can't remember what I submitted, but I just kind of changed it as it went along. And now it's kind of a meta question. Can we conduct meaningful global change experiments in rapidly changing ecosystems? Here's a picture of Bert Drake, who started this global change research out in the marsh many decades ago. And when he started, CO2 concentration in the atmosphere was 344 parts per million. Now it's over 415. So that alone, like, you should see a CO2 effect from then till now. And we're trying to add on top of that in C1. So what is the meaning of that? I think we're doing that. And CO2 change out here is probably the least important thing going on. Everything else is changing too, from nutrients to temperature to sea level. So how do we design these experiments to embrace that? I think the first thing is these dirty little secrets about, whatever, your fire that broke out or this sea level that's obscuring your treatment effects. We need to address those. Those aren't like one-off events. That's kind of happening everywhere. Instead of aiming for pristine and locating your experiment in a stable ecosystem, maybe choose one that's unstable along an invasion front, so that you capture this ongoing change that might be more important than the treatments we're imposing. We can pick sites that are maybe especially subject to strong abiotic change. And I don't know where that wouldn't be really, but these coastal wetlands sure have this dominant driver of sea level rise. But everywhere's got something. So let's just say what it is and formalize that. Okay, thank you.